Hello once again, class, and welcome to another mock lecture. Today we're going to be going over an introduction to limits. So in the last video, we were talking about limits a little bit. Mainly what we talked about is, hey, limits are important. And now let's introduce them a little bit more formally. Now, my claim is that you actually already have a decent understanding about what a limit is already. And to prove my point, let's suppose that you're at a Portland Trail Blazer basketball game, okay? Damian Lillard pulls up for one of these ridiculous logo three-point shots that he often does. And right in the middle of the ball's arc, you sneeze. Obviously, after you've opened your eyes again, the ball has moved its position. But it's not like you had no idea where the ball was when your eyes were closed, right? It's not like the ball blinked out of existence for the moment that you did sneeze and closed your eyes. No, you have a pretty good estimate that the ball was somewhere in the middle of its arc, right? You're still able to track the arc. And so you can make a guess that the ball was maybe here at its apex. That's the idea behind a limit. Okay, this is the concept image that I use for limits. It's a well-supported guess or prediction. Now here's the formal definition, right? The definition of a limit says that the limit as x approaches a of f of x is equal to L if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a on either side of a, but not equal to a. Basically what all of that means is that as we approach the value a, right, as we make x get closer and closer to a, f of x is approaching some value L from both sides. Okay, so like here, as we move closer to a, as x moves closer to a, the y values, the f of x values, seem to be approaching L. As we move closer and closer to a from the x values on the left, right, we get f of x values that are still approaching L. The cool thing is, nothing needs to be happening at a. In fact, the graph could be straight up undefined at a. There could be a jump discontinuity, like in that rightmost graph. In all of these situations, the limit as x approaches a of this function, which I actually didn't label, but pretend all of these are the function f, various iterations of the function f. We can say this for all of them. The limit as x approaches a of f of x is going to be equal to L, because it doesn't matter what's happening at a, it only matters what our y values are trending towards, right, as x itself gets closer and closer to a, right, from either direction. So let's do some examples. All right, example number 1. Let's guess the value of the limit as x approaches 0 of the sine of x over x. Now, you might be like, what? Why are we guessing the value? This is a math class. We should be able to figure out, right, what the limit is. And we will eventually, but right now we're just making kind of supported guesses for the limits as x approaches specific values. 0 in this case is actually an interesting point because the graph is undefined at 0. You can't plug in 0 to this function, so it's not like we could just plug it in and figure out what's going on. At 0, we have to see kind of what the graph is trending towards. And there's two ways, well, there's a lot of ways, but there's two ways that I'm going to focus on in this video for how to guess, right, the limit of a function. One of them is by making a table of values. So what I've done here is I've put x on the top row, the f of x function, or rather I didn't name it, so I should just say the sine of x divided by x function in the bottom row. And I want to look at what's happening as we approach 0 from the left-hand side of the graph, right over here. And then also what's going on the right-hand side of the graph. And I just put 0 in the middle and I put a line here because it's undefined, right? We don't know what's going on at 0 if you just plug it in. So let's just plug in some stuff. So I decided that when I'm approaching 0 from the left, right here, I would look at what's going on at negative 0.5, negative 0.1, negative 0.01, and negative 0.001, and see if I can see if I can find some kind of pattern. So I plugged all of these things in for these x's, and then I just figured out what the output was for that, and this is what I got. Might have been a little bit of overkill to do this one, and we'll see this one as well, the negative 0.001 and the 0.001, because I think this is enough to tell me the story, right? It looks like as we're approaching 0, as x is approaching 0 from the left-hand side, right, from the negative side of the x-axis, it seems to be that the y values are approaching 1. Let's see what's going on the other side. So again, plugging these things into these x's getting an output here. This is what I got for this side. It's kind of like a mirror image, right, of what was happening on the left. So again, as we're approaching 0, as x approaches 0 from the right-hand side of the graph, we again see that our values, our y values, seem to be approaching 1. And so my guess is going to be that the limit as x approaches 0 of the sine of x over x is 1, is equal to 1. Okay, here's another one. Let's guess the value of the limit as x approaches 2 of x minus 2 divided by x squared minus 3x plus 2. Again, 2 here is what I'm going to call a critical value, because at 2, this graph is undefined. And I know that because the second strategy that I like to employ for figuring out some limits is thinking about what the graph looks like. The reason I didn't use it here is because I don't know what the graph of the sine of x over x is. I would have to graph that on Desmos or a graphing calculator or something like that. But this is something that I can do without that technology. Here, I know what the graph of this looks like. This is a rational function. It simplifies even, right? The denominator becomes x minus 2, the quantity x minus 2 times x minus 1, right? I just factored it. So the x minus 2's cancel. And this is just 1 over x minus 1, which is a very basic rational function. So let's review how to graph rational functions. And we can just look at the graph and see what's happening at 2. What does it appear that our y values are approaching as we make x closer and closer to 2 from the left and from the right? Okay, so first things first, I put an open dot at 2 because I know that 2 is not in the domain of this function, right? This thing came from here, and you cannot plug 0 into this, or rather, you cannot plug 2 into this because it's going to make the denominator 0. So we know that there's an open dot at the x value 2, and to figure out how I knew it was at the y value 1, I plugged 2 into this thing, right? 1 over 2 minus 1 is 1, so 2 would normally give us 1 for this graph, but it came from here, and 2's undefined, right? It makes the graph undefined, so I put an open dot there. Okay, so that's how I started this thing. The next thing is I knew that this thing has a vertical asymptote at x is equal to 1. After simplifying the rational function, x minus 1 is still a factor in the denominator. So what makes the simplified denominator 0 would make the graph undefined. That's always going to be a vertical asymptote for rational functions. So a little bit of review there. And then because graphs like to tend towards their asymptotes, and I also know that this thing is never going to intersect its horizontal asymptote, right? Which is when your function is equal to 0, y is equal to 0, is the horizontal asymptote in this case, but multiplying both sides by x minus 1 gives you 1 is equal to 0, which is definitely not true. That's a contradiction. Oh, my pen's on the fritz again. So it never intersects its horizontal asymptote. This was above the horizontal asymptote, and since graphs like to tend towards their asymptotes, I knew this one had to do one of these maneuvers. And then on the bottom, I just plugged in 0 to this function, and I got 1 over negative 1, which is negative 1, so I knew there was a point right here. And then again, same logic as how I graphed the right side. I knew this would not intersect any of its asymptotes and be pulled towards them. So this is what the graph of this rational function looks like. Okay? Again, what's going on as x approaches 2, right? It looks like as we approach 2 from the right, and as you approach 2 from the left, which is really just kind of here, both values seem to be pointing towards a value of 1 again. Okay? So the limit as x approaches 2 of what was originally 1 over x squared minus 3x plus 2 is 1. That seems to be 1 via graphing. So those are two examples of where limits exist, but it is possible for limits of functions not to exist. And here's an example. So example 3, consider the piecewise function q of x, which is graphed below. And it looks like this, right? There is for sure a jump discontinuity in this thing, right? This function is not continuous over its domain, which is, by the way, is something that we're going to talk a lot about pretty soon here. Continuity on domain, that is. The reason why is because this graph, and again, the question here is, what is the limit as x approaches 2, right, for this function q of x? So we're looking at this, we're looking at where the discontinuity exists in its domain. The reason why the limit doesn't exist here is that when you look at the one-sided limits, right, which by the way, are denoted with this little negative or plus sign. So this one is the limit as x approaches 2 from the left. So what's going on as we approach from the left? And then this one is saying, what is the limit as x approaches 2 from the right? That's what the little plus sign is. So we're approaching from this way. As x gets closer and closer to 2, what are our y values doing? And then the blue one again, as you approach 2 from the left, what are our y values doing? Right? What are they approaching in those specific situations? Well, in order for a limit to exist, right? And this is a generalized statement. In order for the limit as x approaches a of some random function to exist, the right-hand limit and left-hand limit need to agree. They need to be the exact same thing. So this says the limit as x approaches a from the right of f of x needs to be the same as the limit as x approaches a from the left. That's actually a theorem. Right, the theorem is that the limit as x approaches a of f of x is equal to L if and only if, is the way that you read that. This is a biconditional statement. The limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, which is equal to that same value, right, whatever L is. That's why we can conclude. So if you can show that these two things are true, then we know the limit in general, right? That's the other direction of this biconditional statement. If we know this, we can conclude this. And if we know this, we can also conclude this. I'm just drawing all over my page now. Our previous two examples, by the way, had this happen, right? For the first one, or I guess this is the second one that we did, the left-hand limit approaches 1, right? As you approach 2 from the left, which really is only happening in this space since there's a vertical asymptote there. But we can still say it, as we approach 2 from the left, for the x values from the left, our y values seem to be approaching 1. From the right, as x approaches 2 from the right, our y values again seem to be converging to 1. They're the same, that's why we can make this conclusion. In the first one, similar story, right? From the left, it looks like we're approaching 1. From the right, it looks like we're approaching 1. This is a tabular format, but it's really saying the same thing as a graph would. So when we're looking at this thing, right, we have to check the one-sided limits. As we approach 2, as x approaches 2 from the left, what does it appear that our y values are approaching? And in this case, I think it's pretty clear that 1 is the answer to that, right? It looks like it's approaching 1. Pretend that's a straight line. Well, what's going on from the right? As you approach 2 from the right, it looks like our y values are converging to the number 3 in this case. Those are not the same. So our conclusion is that the limit as x approaches 2 of q of x does not exist. That's what this means, right? Does not exist. And it's not just these types of graphs that have limits that don't exist. You can have limits that approach infinity, which technically don't exist, but we would actually say, that the limit approaches infinity or negative infinity. You can have discrete points of a graph that oscillate all over the place randomly in a really, really small space leading up to the x value that you're trying to make x approach from either side. And these are all things that we're going to talk about once we start learning some of the limit laws, which are going to be the next video. But that's it for this one. I actually just wanted to have these 3 quick examples. We're going to do a lot more examples in class, but this was just kind of enough to get you started and really knowing this theorem, right? This is kind of the main takeaway for today. If we want to show that a limit exists, we have to show that the left-hand limit and the right-hand limit agree. And if they do, then whatever they're agreeing on is the limit in general, right? That's the theorem. So hopefully that was helpful. If you guys have any questions, feel free to leave a comment or send me an email. Thanks a ton for watching, and I'll see you in the next one.